So good afternoon, everybody. My name is Ludwin Fuchs. I'm a template engineer since 8 years now. And although my day-to-day work here is usually focused more on the control plane side, what I'm going to do during the next 30 minutes is I'm going to dive a little deeper into the template data plane. And, I don't assume people, so at the core of the template data plane is the host identity protocol. And I don't assume, everybody's familiar with that. So what I'm going to do is I'm going to go a little bit into that. I'm going to talk about, what was the motivation behind doing this? What were the goals that the authors had when they worked on that protocol? And I'm gonna talk a little bit about the core key exchange mechanism of the host identity protocol, which is called the HIP base exchange. And it's sort of the central piece of the work where all of the security posture also derives from. And I'm gonna spend a little bit of time talking about that. Gonna tell a little bit about what the assertions are that you can make, the security assertions following out of that protocol. And I'm gonna follow that up with talking a little more about how does this fit all together with the orchestration environment that Brian has shown you? How do the pieces work together? And then I'm gonna move along, talking a little bit about some of the architecture pieces that our technology consists of. Things like the relay, how are we doing port isolation, and also how are we dealing with things like mobility and multi-homing and all those kinds of things. All right. The host identity protocol is essentially an authenticated key exchange. It's essentially it's what is called a Sigma compliant authenticated key exchange, which is basically saying that it's got a perfect forward secrecy. So it's hardened against a lot of typical cryptographic network attacks and things like that. HIP, what's nice about HIP is that it also really comes with a lot of network infrastructure answers. So things like mobility, multi-homing, traversal of NAT, all those kinds of things are either addressed directly in the core standards documents or in related RFCs. So it has a really rich infrastructure environment, which makes it really attractive. What we also like about HIP is that even though it does not really have any reliance on public key infrastructure and certificates and all those kinds of things, it does actually really play really nice along. So if you really like to have those kinds of things, you can, and HIP will work with it. All right, so a few words about the actual protocol standards. So the work on HIP started to get into gear for real around 2003. There is RFC 5201 is sort of the first standards document for what is today called HIP v1. This was followed up in 2015 by RFC 7401, which covers the version 2 of the protocol standard. And so the major changes between the two versions is essentially all around cryptographic agility. So a few of the crypto algorithms were being kicked out. So they gave the boot to things like SHA-1. They added various mandatory transforms. There's a few elliptic curve related transforms that were added, and they also allowed various things to be negotiated that version 1 didn't allow, in particularly around the Diffie-Hellman key exchange. And I think there were also several changes related to the packet processing in the version 2 standard. Now, so those are the core documents. There are other ones that are really interesting to look at. In particular, there's 5202 talking about integration with ESP, which is what we are doing. There is 5207, which is about NAT traversal and firewalls, and we have 8005, which is DNS extension. and there's 8046 and 47 talking about host mobility and multi-homing. All right. Oops. All right. So the sort of the core premise when the authors of HIP started working on this protocol was sort of that in IP networking, the address namespace is kind of overstretched, right? So basically, IP addresses as used today, they have this dual role, right? They have this dual role as locators and as identifier and as identifiers, and so and IP networking doesn't really deliver on both of those roles. So essentially, right, when we're going and when we're typing, you know, keybank.com into our browser or something like that, we expect, of course, that the browser knows how to, you know, how the packets go from the browser to, you know, wherever keybank is and find their way back. But what we also expect is that, you know, at the end of that path is in fact keybank. So, you know, we wouldn't want anybody else to, you know, to get those packets. And so essentially, that's what this whole dichotomy is about. So of course, the internet, you know, IP networking in general has been, you know, really impressive at dealing with the first aspect. So, you know, we've got like billions of nodes on the internet nowadays, and you know, by and large, it works just really great. But of course, the identity aspect of the whole situation has been a miserable failure, right? Which is sort of the reason why we're having a network security industry nowadays. So the people behind HIP, they thought they can fix this situation, right? So the idea they had was, you know, nothing short of, all right, we're basically going to change the network stack, right? So we're going to come along and we're going to have this protocol, and we're gonna have this layer in between the network and the transport layer, right? And so that's going to be our host identity layer, and it's going to deal with all of these problems, right? And you know, this is going to turn untrusted traditional networking into trusted secure networking. Well, of course, nobody wants to change their networking stack in the kernel, right? And the good news is you don't have to, right? Because you know, with our overlay routed solution, you just don't have to do it. So a little bit about the HIP protocol here. So first of all, what is the host identity? So that's the first thing to understand with HIP, right? And in case of HIP, a host identity is simply the public part of an asymmetric key pair. And so, you know, that seems like a good approximation for representing identity. However, public keys are rather large, right? And depending on the crypto algorithm and all of that, the keys also can vary in size, right? So they're unwieldy. You can't really use them in places where you would want to have identifiers for those identities. So you wouldn't want to type them in on a console or something like that. They're just too unwieldy for these kinds of things. So so the people in HIP had what they created what was called a host identity tag, which is basically a 128-bit condensation of the entire public key. And so they're called hits, and so they're essentially what is called an ORCID, which stands for Overlay Routable Cryptographic Hash Identifier. And that is basically a fancy way of saying they look like IPv6 addresses, and they can be used like IPv6 addresses. So an example here is on the slide. So hits in particular, they're built up by reserving 28 bits for a global IANA assigned routing prefix, and then there are 4 bits reserved, which essentially encode the encryption and hashing algorithm used, also the hashing and truncation method used in order to obtain the hit. So that leaves you with 96 bits in that identifier for the actual hash to put in, and that's great. So you have we have these identifiers now. And you can put them into all kinds of places. You can stick them into packet headers. And if you've got your routing set up, you can actually use them as IP addresses on your overlay network, which is exactly what we are doing at Temperate. So with this, we can start talking about the actual HIP base exchange. So the base exchange has two parties. There's an initiator and the receiver, and there are four messages being passed between those, and they're called I1, R1, I2, and R2. And if you've gone through the whole messaging sequence, what you've got is a HIP association. And so I'm not going to go into all the nitty-gritty details here, but I will point out what the roles of all of these messages is, and what the security implications are, and why those messages exist, right? So you've got the first message, the I1, will simply contain the hits of both of the parties, right? And the receiver's hit is actually not mandatory. So implementations actually may allow you to omit that in order. So you could eventually build up things such as a discovery system, where the initiator of the communication doesn't actually know the identity of the receiver. But a typical exchange would have both. Now, the receiver, after receiving this trigger packet, will send a reply, the R1, to the initiator, and this reply will contain, which is like a little cryptographic puzzle. And the point of this puzzle is that essentially the receiver will wants to make sure that the initiator is sincere about the communication. So because he has to spend CPU cycles in order to solve the puzzle. Now the receiver goes off, so works on the puzzle solution, and sends, once he found the solution, he can send the I2 message back to the receiver. And then the receiver, goes along, checks the solution, and if all goes well, and if the solution is right, the receiver will basically send an R2, which concludes the whole base exchange. And at the end of this, you'll have the HIP association. So what are the security relevant roles of this, right? So first of all, steps 1, 2, and 3 essentially consists of a authenticated Diffie-Hellman exchange, right? So in the I1 packet, the initiator will also include his preferred list of Diffie-Hellman group IDs, and basically will also, and then the receiver will send his own group IDs in R2, and then the receiver will also already pick a group ID and will add his own Diffie-Hellman parameters, right? And then on the third message, the initiator will just send his own Diffie-Hellman parameters again to the receiver, and at that point, both parties have a shared cryptographic material that they can draw session keys from, right? So this is great. The other point is that steps 3 and 4 essentially constitute the actual identity check, right? So an important thing to understand with the first and the second messages is that there is no even though the second message is signed by the receiver, it is actually not possible. So it would be basically prone to replay attack, because there is nothing that is really verifiable by the initiator in that signature in terms of identity. But during the third and fourth messages, both participants have shared key material, right? So they can produce things like HMACs and signatures that allows them to actually verify the identity. And so they are also exchanging their public keys in R1 and R2. So they have like a strong cryptographic means to verify each other's identity. Now, I've already said that the puzzle solution is effectively defense against denial of service. So the reason is because during this whole exchange, up to and including the third message, all of the effort is on the initiator side. The receiver essentially can answer to that first initiator message with the puzzles can, for example, be pre-created and simply be reused. and the signed part of that message also contains only parts that never change, right? So the receiver can also pre-create that part of the R1 message. So there's really very little effort that the receiver has to spend in order to deal with these messages. And the receiver also does not need to actually create any state, about that ongoing conversation until he has received the I2 message. So, that all is sort of an effective way to deal with denial of service. Also, what about replay attacks? Well, so that is essentially prevented also by the third and the fourth message, because again, at that point we have shared keys on both sides. So we can add things like HMAX and things like that. So even the first two messages would be in theory replayable by an attacker. The attacker would not be able to bring the whole conversation of the base exchange across the finish line if he didn't actually have access to the shared key. Finally, there is the HIP protocol also talks about preventing downgrade attacks, and basically that is being achieved by sort of prescribing how the first two messages need to be handled. So essentially, protocol downgrade. So in the first two messages, the participants exchange Diffie-Hellman keys and things, or preferred Diffie-Hellman parameters and things like that. So the prevention of that is essentially by how that's supposed to be handled. All right. So do we have any questions at this point?
If Hellman groups are supported.
Yes. Well, so it's one of the things that was added, or so essentially preferred Diffie-Hellman groups were supported in HIP v2. So the initial version of the protocol did not allow that. All right. So just a little bit of how the tempered solution has a little bit of a slant here on this. So one of the things I mentioned earlier already is that we do actually include certificates in the base exchange. So all the tempered air walls get provisioned with certificates. So and the conductor will distribute these certificates to the air walls. So as part of the key exchange, all of the air walls will check the certificates, not just the public keys that comes from the other side. So we've added that. So in terms of where we are with V1 and V2 of the base exchange, so we're sort of in between. So we are supporting all of the newer crypto algorithms. So we have AES 256. And all the mandated crypto algorithms are supported, but we do not have all of the features of V1 in place at this time. All right, so now after the base exchange completed, we have a ShareTip Association between two parts. So what's happening now? So one of the things that was also going on during the base exchange during the last two messages is that the parties exchange ESP parameters, right? So basically, the security parameter index and also the preferred transform is all exchanged also as part of the HIP exchange. So at the end of that, both parties are essentially ready to start sending ESP packets to one another. And just to come back, I know we had this question during Brian's session earlier on. So what are the kinds of packets that you see on the data plane? Well, you basically see two kinds of packets, both of which are UDP encapsulated. But in the first case, you see actual HIP packets. So HIP have their own HIP have their own protocol ID, right? So you see HIP control packets, but the vast majority of packets that you would see on your network would be UDP encapsulated ESP packets, and that's where the actual data traffic is being carried along.
So that raises a question that I kind of have about this overlay underlay setup that you've got. What's the reachability in the underlay network required to be able to set up this overlay network?
So you have two options, right? So if you have no relay, we have the relay architecture. Without a relay, you have to have port 10500 reachability between one of the peers in order to build a tunnel with another peer. So you can traverse NATs easily that way, but as long as you have the HIP port being reachable from one peer to another peer, you can build a tunnel.
Right, because one of the use cases I think we discussed earlier was around operational technology networks and like SCADA networks and so on, where part of the protection we had was that it wasn't actually connected to these networks before. But now we have to have some kind of IP reachability into a network that previously didn't actually speak IP.
Okay,
so I'm just trying to understand how do we do this in a safe way so we're not actually increasing the attack surface while we then try to put this overlay network on top.
Right. Yeah. And as we mentioned, with the relay in the loop, you really actually need to have no direct path between the two peers because you can go through the relay.
Okay.
All right. A few more things actually to mention here is that also as part of the HIP protocol, additional sorts of packets. The most important one is called the HIP update packet. It's also a packet that provides strong assurance. It has an HMAC and it has the signature and all of that, and it allows the two peers to do things like rekeying the session key or notifying each other that their underlay IP addresses have changed, and all those kinds of things are being carried over HIP control packets such as update. What I'd like to say a little bit about our ESP again is so Temperate uses ESP in tunnel mode. So we tunnel everything, but actually we tunnel more than standard ESP tunnel mode does. So we also include the Ethernet header in the encryption. So this leaves us with roughly 90 bytes of packet overhead. On the data plane, also, now that you look at the architecture here, so we've got tunnel set up and we have this whole identity framework. So what does that actually mean, right? Well, so it's a little bit different between our agent platforms and our gateway platforms. So for our agents, the identity really only covers the agent itself. So trust does not go beyond the device that actually runs the agent software. This is different from our gateways, where the gateway identity is really sort of like a placeholder for multiple devices behind that gateway, or like it could be an entire network, right? And so also what we also add with the port isolation is that we also allow you not just to north-south segmenting of your network, we also allow you to go east to west on a single gateway, and it's all controlled by the conductor. So basically, this is really the place where the conductor orchestration comes in, right? Because host-to-host identity is only half of the picture, right? So what comes on top of that is the entire policy that gets pushed out from the conductor, and so essentially for any packet that hits the HIP daemon, we basically can tell, by looking at the source and the destination IPs, is this packet actually going to go in the tunnel or, out of the tunnel? And it's only going to do that if we have end-to-end policy for that.
Just a quick question regarding scalability. How many of these sessions can you have in parallel? What is memory, or what is the limiting factor, and how large can you scale?
So are you're talking about like how many tunnels from a single air wall?
Exactly.
So we can scale up. Actually, I have the expert here in terms of performance questions. So I'm gonna bring in Dustin here. Dustin is the person who can answer this.
Yeah. So we can scale. Depend on the platform. Memory footprint. The footprint per tunnel is relatively small. We ship with a 1K tunnel limit, and that's just sort of but that's configurable. And then we'll bump it up to, we've bumped it up to 4K. 4K or plus. But most of our customers aren't looking for that. The environments we're seeing are usually several hundred is the upper limit there.
All right, thank you. Okay, any more questions? I think I'm going to have to start flying along here. So a few things here that I'd like to bring up. So first of all, how, okay, let's go here, switching slides here. All right, so we've talked about identity. So how does the identity actually get on the air wall, right? So that's one of the things where we have a process for. So essentially it goes like this, as the customer fires up the air wall will go along, create a key pair. And the customer will go to the air wall, pair it with a conductor, and as soon as the air wall connects to the conductor, it will send a certificate signing request to that conductor. And so what we have here at Tempered also is an identity server. So it's essentially like a provisioning server that we expose on the internet. And so as the air wall shows up in the conductor UI, the customer can, first of all, can say, has to actually allow it to go through there. And then the conductor will communicate with the Tempered identity server and get a signed certificate from Tempered, and that's what's going to end up on the air wall. So from that point on, the air wall is provisioned. A few things about what's inside the box. So this is essentially a very, very high-level view on the gateway architecture, on the air wall gateway architecture. So we're running OpenWRT as the base OS essentially. So it's a firmware. We're pretty happy with OpenWRT. OpenWRT is a pretty nice ecosystem. You can boil it down very small, and it has already all of the network management features and all the kinds of things that you'd like to have on your base OS. So we've been happy with it. So on the architecture side, so essentially you have on the left you have the overlay side, and on the right you have sort of the underlay side. So it's just a schematic here, but essentially, so we have what's called port groups. So those are essentially Linux namespaces that allow us to put the entire interfaces of those ports into a separate namespace, and so they're isolated from one another, and so it makes it easy to have port isolation going. So we're basically supporting two types of ports there. One is what we're called hybrid layer 2, layer 3 ports. So essentially, if you wanted to have an overlay network that spans a LAN on either side of the tunnel, then that would be the kind of port group configuration that you would use. And we have routed only mode. So basically, if you wanted to have separate subnets, behind your air walls, then that is the preferred way of configuring those. Now, the port is to talk with the actual HIP daemon on the air wall. There are tap interfaces. So essentially, they're bridged in case of the hybrid ports and unbridged in the other case. And inside a HIP at that point, it's really all pushing packets around and encrypting packets coming in from one side and pushing them out on the other side. And the other important part here of the architecture is we have a control daemon. The control daemons, so the most important role of that is to connect to the conductor and basically get all of the conductor policy configuration, and essentially that's the role of that. The control daemon also runs things such as the monitoring framework and the link managing framework, and it's also responsible to do all of the OS level configuration jobs. A few things about the relay. So the relay is Tempered's answer to defeat double NAT. So essentially the way this works is the conductor provides what's called relay rules. So any air wall can be told to have, various types of relay connections to peer air walls. So from the perspective of a single air wall, you end up with basically multiple relays that could be used to talk to a peer air wall. So we basically have to figure out which relay would be the best to use in order to have a base exchange. And so we have two approaches to do that. One approach is what we call the shotgun approach, right? And so using that approach, you have, all the air walls essentially continuously try to build HIP tunnels. And while they do that, they actually send I1 packets to each of the relays. And the relays really aren't involved in any of the base exchange. But what they do have to do is they basically learn the mapping of the identities and the IPs and ports of each of the participants. So the relays know, which air wall has which IP address and all of that. And then, once the other approach is what we call relay probes. And relay probes mean that it's a more lightweight approach, so that where each air wall sends a special I1 packet to each of the relays that it has. And the relays will just respond with an R1 packet, and the air wall uses that just to time the exchange and just keeps an exponential average. And then it's just going to try the fastest relay first in order to do the base exchange. All right, I think I'm thinking I'm at the end of the time here. How am I doing here? Can I? 5 minutes. 5 minutes. Okay. So last thing to talk about here is our link managing framework, right? So one of the nice things about our air walls is, so for example, we have models that allow you to equip them with dual SIMs. So we have air walls where you could basically have a sort of like a remote HA configuration for those kinds of air walls, where you have one SIM configured with one carrier, and you have like a failback SIM to talk to a different carrier. And we have software on the air wall that will sort of monitor the network and will basically provide failover. And the way we allow you to do that is we have what is called these failover groups. So basically, failover groups can be used to sort of put in different types of link. They don't have to be cellular. You can have any type of underlink you would like. You can group them, and you can assign them priorities, and you can also assign a traffic class. So maybe you want different failover groups for different types of traffic. So for example, you could have a different group for the conductor connection, and you could have another group for your data plane connectivity. And the link manager will basically cooperate with the monitoring framework, and do things like run pings and find out which one of the links actually works and which is the one that we should be using now. And so this is giving you fast failover, and many things like that is just a must-have in many industrial application scenarios. We've had customers who had like factory applications where the air wall was part of moving robots that had to be wireless, but then all of a sudden they have to be wired, and so failover in those kind of situations is a really nice feature.
But this is pure active passive, yeah?
No, it's actually active. So both of the links are up at all times, or however many links you have. So it's active. It's basically just a matter of the link manager telling the control plane, use this interface instead of that. But it's not like the link needs to be wound up.
And you have kind of a load sharing as well, that you say some of the connections uses link 1, the other link 2 to optimize the bandwidth.
That's a good point. No, I don't think we don't have that at this time. No.
Okay.
It was mentioned earlier about the sort of the smaller, almost throwaway gateways. Are any of those PoE enabled or PoE pass-through?
I think we have, yes, I think we have PoE enabled gateways. I'm not too familiar with the details. Does anyone here in the room know about it? Yeah. So, all right. So I've got one of these here sitting right there. So this is one of our newest models. And yes, it is PoE enabled.